The sampling distribution of the sample mean we're talking about today. Yesterday last time we talked about the sampling distribution of the sample proportion. Now we're talking about the sampling distribution of the sample mean. Okay, the sample mean is denoted X bar. That's the sample mean. That should be familiar. So another one of the major tasks of a statistician is to discover the mean or average of a certain variable in a population. So if we're asked to find the average of, for a population, we call it mu. So for an example, we're trying to find mu, the mean income of U.S. residents, the average income of all U.S. residents. Okay, what's the only way you're going to do that? Census, that's it. That's the only way you're going to do it is a census. Okay, or the mean reduction in cholesterol for patients using a new drug. Okay, you're going to have to find every patient using a new drug to figure that out. That's why they do clinical trials before they allow doctors to offer new drugs to people. Okay, you do trials to find sample means. How much does this drug help or not help? Okay, so we want to know mu, or sometimes we do know mu, and we base our sample on that mean. So we're going to find a new sample. Okay, X bar is from the sample, mu is from the population. So again, unfortunately, without conducting a census, we're not going to figure out either of these. And these are called the population mean. That's mu. That's the variable we use for the true mean. Instead, statisticians will estimate the mean by taking a sample and computing the sample mean. Which is X bar. So those are the difference between the two things. Now last time, if we look back at the notes, everything was dealing with p hat. Okay, we found the sampling distribution of p hat, and which we could represent it as a normal model. So today we're finding the sampling distribution of X bar, and we're going to use a normal model after we check conditions. So here are the general properties of the sampling distribution of a sample mean. So in other words, I've got a big population, and I have taken a sample and calculated the mean. Okay, a sample of size n. So let X bar denote the mean of the observations in a random sample of size n. I just stated that. From a population having a mean, a true mean, mu, and a standard deviation, sigma. Denote the mean value of the X bar distribution by the mean of X bar, and the standard deviation of the mean distribution, the sampling distribution, by sigma of the sample. X bar, remember, is from the sample. Mu is from the real population that we don't know. Then the following rules hold. So these are formulas that we're going to need to memorize, and then other things that we'll need to know, and then conditions. So the first thing is that the mean of X bar is just the mean of, is just mu. It's the true value. And the standard deviation of X bar, the sample, is the true standard deviation divided by the square root of n. What's n? It's the sample size. N is always the sample size. That's been since chapter 1. N is the sample size. So sample size, you just divide by the square root of the sample size. Take the true standard deviation divided by the square root of sample size. So these are the formulas. These are the things we're going to use to change X bar into normal. So X bar is approximately normal with a mean of mu and a standard deviation of sigma over the square root of n if the conditions hold down here. If the conditions hold. The sampling distribution of X bar, the sample mean, is approximately normal with a mean of mu and a standard deviation of sigma over the square root of n. The only difference between X bar and a regular normal model is dividing by the square root of the sample size. Okay, so now two more things to talk about. These rules hold for a sampling distribution of X bar. Sampling distribution of X bar. Okay, so when the population distribution of X bar is normal, of x, of x is normal, the sampling distribution of x bar is also normal for any size n. So what does number 3 mean? Number 3 means that if the mean income, okay, if the mean income of all U.S. residents is normal, then any sample I take of U.S. residents and find their mean income is also normal. If the whole population is normal, any sample I take from it is also normal. Does that make sense? Okay, that's what number 3 is saying. If the whole population is normally distributed, then any sample I take is also normal. And this next thing, which is very important, you should have actually already watched a video on the central limit theorem. There's one on Canvas called Central Limit Theorem. And it's also in the reading in your book. It is important that you know it because they'll have questions on it on the AP test. So I'm going to explain it a little bit. Actually, down at the bottom of your notes here, if you look down at the bottom, I can't get my computer to pull it up because Java isn't working right now. But you can try this website, the second one. The other two, I have to find new websites because they've done away with those. I look for websites from colleges usually because their grad students develop neat little things. They're called applets. They're just little animated things that demonstrate for you like what different concepts mean. So this one actually is a really good demonstration of the central limit theorem. Okay, and the central limit theorem is basically just taking what we just talked about a little bit further. The central limit theorem says that as long as n is large, okay, as long as n is large, okay, and we'll define what, and large, if you go down here to checking your conditions, large sample size is the third condition for today. What does n have to be bigger than? 30. So a large sample size isn't that big, is it? You wouldn't consider 30 to be huge, would you? No. So a large sample size, when you have a large enough sample size, any sample, any number of samples that you take and find the mean of will become normal. And this is the key, even when the population is not normal. And this little applet down here, if you go there and choose simulations demo and then sampling distribution, it does have instructions. It tells you exactly what to do to demonstrate it for you. It's kind of a nice little thing. If you start out with, and I'll just draw a little picture on here, if you start out with a skewed population, okay, we've got a skewed population, and it doesn't matter which way it's skewed, okay, so I'm just going to make it, this is nice and skewed here. So there's a skewed population. It doesn't matter which way it's skewed. And what I do from this population is I take repeated samples. I take repeated samples. So I take a sample of 5, and then I find the mean. So take repeated samples and find the mean. Find x bar. So I take a sample, so this will be my first sample. I take a sample, and I find the mean. Okay, and I get that the mean is right here, and so that's one person. I mean, think of these as dot plots, really. These are like dot plots, like different, or a histogram type thing. So I take one sample and I graph the mean here. So along the bottom, I'm graphing all the means. So then I take another sample and I graph the mean. And another sample and I graph the mean. And a third sample and I graph the mean. And if I do that, what I will usually find, what the central limit theorem says is that if you take enough samples and start plotting those samples, what eventually happens is that the shape of the samples will become normal, even if the original population is skewed. So you take a sample, find the mean, graph the mean down here. Take a sample, find the mean, graph the mean down here. The means, as long as you take more than 30 samples, the graph of the means will become a normal model. So that's what the central limit theorem says. Okay? And you'll get that reinforced in the reading and if you watch the central limit theorem video. So the central limit theorem says that when n is sufficiently large, meaning greater than 30, the sampling distribution, a distribution is just a group of numbers. So a sampling distribution, it's data, okay, it's a bunch of data. So a sampling distribution is data that comes from it comes from samples. So in this case, it's the mean of a bunch of samples. So when n is sufficiently large, the sampling distribution of the mean is well approximated by a normal curve, even when the population is not normal. Now you don't really need to worry about that a whole lot. You need to know what the central limit theorem says, though. Okay, they've already discovered it and figured it out. All right, so now let's look at the conditions. Every single time you do a problem that asks you a probability question, okay, find that what's the probability of this, and it's n is something, it's a sampling distribution problem, and n is more than 1, then you have to check your conditions. Okay, just always check conditions before you use a normal model, especially if it's for x bar or p hat, unless it's a normal model on a normal problem. Okay, so the data is from a random sample from a population of interest. Didn't we already have that condition last time? Okay, what condition was that? What was the name of that condition? I gave it a name. Casey, what name? What did you say? Yep, randomization condition. This is the randomization condition. Okay, so you would have to, in your problem you'd have to say, well, it's stated as a random sample, or I'm going to assume it's from a random sample of voters, of apples, of whatever you're talking about, U.S. citizens. Okay, the second one is the independence condition. It says independent there when we're defining it, so, and the 10% condition, but they're the same thing. So you have to assume that whatever n is, you have to, in this, when you're checking this condition, you have to assume that n is, whatever n is, like say it's 400, it's less than 10% of the whole population. And then finally, this one is different. When you're dealing with the sampling distribution of p hat, this large sample size condition, or this success failure condition, is n times p and n times q, but it's not here. What is it here? What does it say? N is greater than 30. The sample size is greater than 30. Isn't that easier to check than n times p and n times q? Yeah, you don't have to do any math. You just say, oh, well, n is 25, so it's not. Okay, so what do you do if it's not? Or the distribution is from a normal population already. So the or is really important here. If it's less than, if your sample size is less than 30, it's okay as long as it's from a normal population. All right, and this stuff down here, this is just using rules from chapter 6 showing you where these formulas come from. So, and we already talked about these on the bottom. So now we'll move